This is a bit of a grandiose title, and I did that on purpose because I wanted to get as many people in here as possible. So let me just start by introducing myself. My name is Jason Fox. I'm the co-chair of the Spatial Mapping and Positioning Working Group in OpenAR Cloud. I'm also the head of spatial computing at a company in Dallas, Texas called Hypergiant Sensory Sciences. Previously was at Microsoft as a software engineer working in spatial computing for the past 4 or 5 years, doing a lot with enterprise customers, figuring out how to build scalable mixed reality AR solutions. So I'm going to start by giving you some background on OpenAR Cloud, just very briefly. So this time last year at AWE EU, OpenAR Cloud was officially formed by several folks actually in this room. Jean-Eric is the managing director. He's sitting right here in the front. February of this year, we formed our first working groups, and these were people who showed interest in helping out, and we started talking about what our work was actually going to be for this group, or for this organization. We hustled, I think is a good word, and we published a report, State of the AR Cloud report, back with AWE in Santa Clara. We also hosted our first AR Cloud symposium the day before Santa Clara, AWE. It went off very well. We had some amazing conversations about the challenges and the potential of AR cloud technologies. And then fast forward to today, we're working on publishing some updates to the AR cloud report as things have changed over the past 5 months. And then we are working on a draft of something we call the Spatial Grid, and that's what I'm going to tell you about today. So, a little bit of a disclaimer, this is very much a work in progress. That's an actual photo of me working after hours every night. So, getting into the why, I think this is very important. First of all, we kind of view the AR cloud technologies as an economic engine, very much like the internet or the web has been for the past 25 years. And we think that new types of interaction, new ways to make money will come about as AR cloud technologies mature and start to coalesce into a strong ecosystem. To do that, however, we believe that you have to have an inclusive ecosystem where people are allowed to bring their own devices to it and also their own data. And I'll get into that later on. To be inclusive, you have to share, right? You have to have standards that allow the sharing of an exchange of data between parties, between entities within this ecosystem. And to be able to share, you have to standardize. And so that's the goal of OpenAR Cloud, is to help that standardization come to fruition within the industry. Of course, along with that, we have security and privacy concerns to take into consideration. Very important, given the access spatial computing has into your personal life, from the sensors, the activity that you're doing as a person, and the potential for you doing it out in public places. It's very important. So what is the spatial grid? I just think of it as the power grid, kind of. Like it's a utility, the proposal of a utility to enable the shareable map of not just geospatial, but indoor spatial as well. And so you can map the inside of a building with a standardized mapping system, and then position to that map with any number of positioning systems. And it just works for all of these positioning systems and for everyone on every device. So this is Jean-Eric came up with this kind of description of what we're trying to do. And so standardized encodings, protocols, and data framework for the machine-readable world. And that's the spatial grid part of everything. And here's a layer diagram that we shared in May. You've probably seen some versions of this before in other presentations where we have a static reality layer. Is this point? Yeah. Which is basically the static map of everything, like where things are located in the world. And those are things structural to the world, like buildings, right? And then the rooms within their buildings. And then on top of that, to know where everything is that's in motion, that's dynamic, moving around furniture all the way through the people that are moving out of space, you have to have this real-time layer capability. And so those are the two biggest challenges that we're hoping to solve with the spatial grid architecture. So one of the fundamental things, the fundamental standards to all of this is something we call geopose. And it's the precise position and rotation of something in the world. And it's relative to the world. It's not just relative to this room. So for example, I have a geopose right now, and each one of you do as well. And so if you were to take the GPS coordinates approximately of where you are in this building and then refine that down into a three-dimensional position with rotation, then you would have your geopose. Okay? And it seems like a very challenging, if not impossible, thing to resolve. However, we believe that it is possible, or it will be possible soon, and is going to be necessary to power this kind of great shared experience, I think, that a lot of people are wanting to see come to fruition. So let's start with maps. And how mapping kind of fits into this and plays into this, and how we think we can standardize a map. So we'll start with talking about topographies for a moment. So we have the current topographies that people generally associate with maps. Terrain, roads, transit, buildings. It's how we navigate through our cities, between cities, from our home to a place, et cetera, right? And humans have been doing this for hundreds, thousands of years. And it's kind of a well-established school of thought at this point. So we have these new topographies now that are going to play into mapping. Some of them are not new. They've been around for a long time. BLE beacons, Bluetooth Low Energy, right? Wi-Fi access points. We now have 5G, promises some capability of positioning now. And then we have 3D geometry. And when I say that, I'm talking about the building geometry. And so the geometry of the building that we're in is relatively static, right? So unless it undergoes some construction or it's reconfigurable in some way, the 3D geometry of a building is static, right? So visual features, that's another visual positioning systems, such as what we have some of them here today, like Escape.io and others, Visualix, magnetic positioning. If you guys haven't heard of that, you can detect the magnetic signature of where you're at that's tied to the magnetic fields of the Earth, right? So one of our biggest partners and earliest partners is Open Geospatial Consortium. And this group has been around for quite a while, and they've been working on standards for spatial positioning in computing for a long time. And if you're familiar with the way databases work in storing geospatial information, they published the simple features standard, which is used in databases today. They also published something called coordinate reference systems, which are standard in translating between different mapping coordinate systems. And so we have a pretty strong partnership with them. One of our founding members is one of their standards leaders. And so we've been talking to them about how to solve some of these challenges. And so let's talk about a little bit. So coordinate reference systems, they have this great thing called geographic markup language. And so it was originally intended for defining just like geospatial geometry, but it's been proven useful to define other types of geometry. And so there's one called City GML that gives you a more refined, accurate geometry of the buildings and other features in cities. So if you guys have seen the extruded geometry on something like Google Maps in 3D mode, where they've simply taken the profile from the satellite imagery and then just extruded it up a height, right? It's not incredibly accurate representation of the building. However, with City GML, you can have that accurate outside geometrical representation of the buildings. You also have topographies and the semantic relationships between buildings and the features that are around them on the streets, park benches, bus stops, etc. And so you kind of start to see its, original use cases have been around like smart cities, for example. But it's a good, well thought out standard for mapping the geometry and the semantics of a city. And so the next one is indoor GML, which is based on GML and City GML as well. However, it takes the concepts of City GML and moves it indoors. And so you almost can just think of the two spaces separately, and the needs are different. So the geometry is very much the same, right? You're just moving inside. However, it is also cellular geometry, and so you've got rooms that comprise the overall geometry. And so this format is intending to account for that, and it also accounts for how you move about the indoors of a space. And so this is a screenshot that I took from running an actual example from that TU Munich built, actually. And they have a website up where they're showing off the work that they're doing with City GML. And you can see, not only does it have the geometries, but it has these lines that kind of represent the semantics between buildings and things. It's not incredibly noticeable here, but if you were to dig into the data file, you would understand what these things are. So GML is typically based on XML, and if anybody's been working with data exchange formats, pretty much the industry's moved on to JSON at this point. So there's been work to move on to JSON formats for these, and so there's a City JSON. The new standards for GML are going to support JSON out of the box, and so it's just much more compressed, more efficient, for communication, which is going to be critical for scalable performance solutions. So this is an example of indoor GML. So this is the same building. This is actually the 2D floor plan of, I think it's the first floor of this building. And so you can see the room geometries are shaded different colors. But they also have these lines that connect through the rooms. And this is basically the logical pathing topography of the space, like, you know, where the doors are in and out of a room, and then they're anchored to a node that represents the center of a room, saying that you've kind of arrived into that space. But it also has connections between floors. So if you have a staircase or an elevator, you can have that logical connection, right? And so you can start to see that we're defining not only geometry, but the way to move about in a space, which is going to be, you know, critical for things like navigation. One of the important concepts in indoor GML is you have the geometry, and I was kind of alluding to this before, but you also you create this kind of node relational graph of all the rooms and those lines I was showing you. And you create this, just due to the fact of the laws of geometry, this Poincare duality effect when you have a closed manifold system related to the closed geometry. And so you get a one-for-one match between the space and then the kind of logical flow through the space. And you can apply this to different types of topographies, right? So Wi-Fi sensors, RFID, I don't know anybody that uses that anymore, but BLE, and other types of locationing systems or positioning systems. It also supports this kind of multi-layered space model approach. So you can see we have the kind of the geometric topography space definition. You have Wi-Fi sensors, RFID, and they map to each other, right? So you can layer these on top of each other. And so no matter what positioning system I'm using, I can get to the same place, get to the same location. So the goals for maps, we want to standardize how we define geometry for locations. We want to make sure that no matter what positioning system you're using, and whether or not it's on a mobile device or it's on an AR headset, when you go in to a building or you're walking down the street and you localize, you get the same data. So it doesn't matter what device you're using or what positioning system you're using. We have those new types of topographies that are going to help us do that, and we now have a data format that allows us to layer them together in a logical fashion so that they all line up with each other. We can resolve geopose from them. So if I don't have geopose and I use, let's say, a Visualix positioning system here in this building, in this room, and Visualix has said, hey, I know what geopose you're associated with in this room, or it's got a definition of geoposes for this room, then it can localize you out to the world, right? And so then now you have your exact position in the world. And they can also then query the map. And the map is going to consist of much more than just geometry, and I'll get into that in a few minutes. It can also be queried using geopose. So if you already have geopose, you just simply query the map. Right? It's very similar to global positioning, GPS, and the way that it works, say, like on Google Maps. If I have my position on the map, and then I can then go into like querying points of interest around me, for example. So speaking of positioning, let's talk about that for a minute. So we have different types of positioning systems today. We have GPS. This is the one that most people, I think, are familiar with. We have visual positioning systems. So SLAM-based visual inertial odometry, persistent anchors, so something like Azure Spatial Anchors or Google Cloud Anchors. SLAM seems to be the more prevalent today. The more accurate, you get closed loop navigation through space and start to realize some good accuracy with it. Indoor positioning systems. Like I said, you have Wi-Fi, Bluetooth low energy beacons, 5G, magnetic. Ultra wideband is something intriguing now with the onset of the chipset in the new iPhones. They'd include this capability. It's been around for a while, but it's been kind of prohibitively expensive and not really thought of as a solution, I think, in a lot of cases. But now that iPhones have it, I think that's going to drive adoption more. And it's accurate. I've ordered a dev kit for ultra wideband myself to see what it does, but I've been told it's accurate up to about 5 to 10 centimeters, and we're talking about locating someone inside of a space that's pretty accurate. So the positioning process, as we envision it today, and it might change, is you have your positioning systems that your device is using, and if you kind of know where you are, or you don't know where you are, you can kind of query the map and say, hey, here's so let's say we're using a visual positioning system. That has typically a point cloud associated with it that defines some rough geometry, some shape of the space you're in, right? And so there's some kind of interesting math that you can do to align that and query and find matching geometry, right? And so theoretically, you can then say that I'm in this room because now I've matched the geometry of my visual positioning system and the way that it understands the space to the geometry of the spaces that I know that are inside this building because I downloaded this building when I walked into it because of my GPS position. Okay? And then that could ultimately give you geopose. And inversely, if you already know geopose, you just query the map. Right? Indoor-outdoor transition is going to be a critical piece to the success of this. So if I'm outside and I'm walking down the street and I'm using something like GPS or visual positioning, I can pretty, accurately get back the city GML of the location that I'm at. If I walk up to a building, there's a concept in GML of this anchor node. And it's meant to define the transition between outside and inside, or outdoors and indoors. And so as soon as I pass through this node, I can then begin to download the indoors representation of the building that I just entered. Right? And then I can start keeping myself aligned to that geometry, to that map, using indoor positioning. And this is all related to geopose and maintaining where your geopose is. And here's that duality again. Just wanted to remind you. We're moving kind of quickly. We'll have some time for Q&A. Let's talk about modeling for a minute. A few minutes, hopefully. So we kind of have the sense of mapping down at this point. I'm sure it will change probably quite a bit over the next few years as we continue to work to define these standards. But those are our thoughts today and how this could work, right? However, it doesn't solve the problem ultimately of if I wanted to augment, this podium, right? So how do I know that this is a podium? How do I know what it's capable of, where it's located, and those types of features that ultimately a kind of, as Charlie Fink would say, a world painted with data would function, right? And so we need something, some method of doing that. And so that's what we refer to as modeling, or modeling reality. And so in these, if I were to kind of come up with an analogy, the points of interest on a map, there's different types, right? There's restaurants, there's sightseeing places, museums, shops, right? And I can filter those based on what I'm interested in seeing on the map. And so we have this concept of modeling, which is essentially, it's based on graph theory, database graph theory, ultimately. And so we have these concept of nodes, and then there's the properties within each node, and these are going to be related to the object that that node is representing. Again, I'll just go back to the podium. This podium would have its own node, and then within that node, it would have things like geopose, the geometry definition of it for accurate placement and accurate shape representation, and then it could have other properties that are unique to describing what a podium is and what it's capable of. Same thing with the projector, myself, right? Other objects in the world. And then also very critically, the relationships between each node. So we have spatial relationships. And that's how far something is from other things in relation to the bounds of this room that we're in, the volume that we're all occupying right now. And then we have the semantical relationship, which is going to help us understand how to interact with the world. And this is very critical, we think, because if we want computers to accurately moderate our world in, say, augmented reality systems, then it needs to understand the world in a very similar way that we do. And so we call this the machine-readable world, and we want to have computers to have generally kind of almost a human understanding of the world and join us in that consensus of reality that we all, or most of us, share. And so this is purely a thought exercise that I did that I'm going to take you through real quick. This is obviously an image of an intersection. It's fairly busy. We have people, we have crosswalks, we have streets, sidewalks, there's a trash can, there's cars active through it. And so you can label the entities in this, and these will end up being nodes, right? There's a signal here. And they all exist, they're all things, but they ultimately have different properties to them. But the one thing they do share is that they're all occupying the same space, right? So they all have a semantical relationship with each other as well. And so I took that labeling exercise from the last slide, and I wrote some cipher and created a Neo4j representation of it in a graph database. And so you can see how everything has its own node, and then it has a relationship in semantics. So the silver van is on sidewalk 2. That's not incredibly accurate. It's actually in the parking lot that's attached to sidewalk 2, but it's pretty close. Person 7's on sidewalk 2. Intersects with an intersection. It intersects with the road. So you can kind of start to see that if we could give a computer this understanding of a scene, then it can help us moderate the world in a very accurate way. And so in order to create these models, we think there would be different types of inputs. So there's the manual modeling. That's just simply somebody taking a tool set to build a model like I did with the database, and then putting it into the system, the shared architecture, the framework. And I have a feeling that, we'll start off that way, as most technologies do. But we'll get smarter about it, and we'll have automated ways of doing it. IoT is one way, right? So IoT, we have all these connected things around us every day now, and they're capable of reporting their state to us as they sit and as they change over time, and so you end up with a temporal factor as well, right? And so you can kind of start to put together a real-time representation of these things that are connected through IoT. Media, imaging, things like that, and then we'll user input, geopose, and then this very interesting academic work going on today using neural networks to kind of dissect a scene from imagery and understand what's in it and what the semantics are between those objects. One quick user input is like if I were to, if I'm using today HoloLens 2 has hand tracking, and I have a virtual digital twin or copy of the podium, and I grab that and move it, or I change state, that's user input into the model. So with that, we have a concept we call reality modeling language. And at this point, it is just a concept. It's something that we came up with between May and today. So it's something that we think is going to be critical to this framework. And it's a standard that we're looking at publishing out of OpenAR Cloud, sometime in the near future. So the basic concepts, so we have a multi-layer distributed graph language, like I showed you in the graph database that I built, and so scaling that out in some fashion. Having it layered, I think, is going to be important. If you go back to the imagery, the diagrams that say we had here, but also like Magic Leap and Facebook have published in their concepts of layering data, right? You could use this data format to comprise those layers, right? And so having them layered on top of each other or adjacent to each other, almost in a channeling type representation, I think is going to be important. Also, static and dynamic nodes. Static would be things that don't change very often, or not at all. And then on the real-time dynamic nodes, and so these are things that are going to need to be updated very frequently, like people, cars, pets, things that are moving around a lot, or some. Nodes represent a stateful model of a real or virtual entity, and so you end up with a pairing of a real object or a virtual object, or one or the other, so you don't have to have them paired together. Nodes can represent the synchronicity between real and virtual entities. So saying, like, if I moved the podium along the stage, I would expect its geopose to change in the model, in the map. Nodes will have their geopose of that object stored in them, so that when I come in and I go back to the positioning and the map of the world, I can load everything around me that has an approximal geopose to where I'm standing. The connections between the nodes via their semantic and spatial relationships, as I pointed out earlier, we think is going to be critical. And then storing other arbitrary properties about that object. I mean, there's no common language really other than the way that we communicate verbally with each other to describe the things that we see in reality. And so it needs to be kind of unstructured and open-ended in how we do this. And we don't know exactly how that's going to pan out on the consumer side of the data, but you can kind of, we kind of imagine that we could create this kind of natural language interface that says, return everything in this room that has properties X, Y, and Z, or has the keywords X, Y, and Z in its properties, right? Interoperability. So this is something very important to us, because the last thing that we want to do is own this map, own the data. We don't want to own any of it. We do, however, want everyone who is interested in building and owning an AR cloud to be able to share their AR cloud into the system. And you can imagine if I own a building and I hire a vendor to come in and create an AR cloud inside that building, and then I decide to drop that vendor and go with another one, what do I have to do? They have to come in and remap the entire building, right? But if I have a common map that works between vendors, all they have to do is come in and set up their positioning system. They don't have to worry about mapping anything, right? So that comes to bring your own data. This is, we think, going to be critical. We don't want to look under the hood of anybody's technology. We don't want to dig into anyone's IP around positioning. That's theirs. We want them to keep building that. We want them to be able to make money off of that. And then we just want to invite them to work in a standardized way, very much like the web does today. And so choosing the vendor for where you're hosting your website, the different website framework that you're using to build your website, right? It just works. And so we have this interoperability vision that one of my senior architects on my team came up with. And so AR Cloud Provider 2 and 1, they have different capabilities. They register their capabilities and the interface, and then the clients are able to interact with them in the same ways, right? And then they're geographically or spatially separated from each other as well, I think, and I'll get into that in a minute. But this is kind of some early thoughts around how this interoperability is going to work. So it'd be spatial partitioning. It's a concept today in something like databases or data storage. But in this case, like, it's literally spatially partitioned. Like, the building you're in owns the data, or their hired vendor owns the data, right? And it could be hosted on the edge, it could be hosted somewhere centrally. We think for scale and performance, it's probably better to host it on the edge so that you can take advantage of those very low latencies that the edge and now, the coming 5G capabilities will provide. But also, kind of security-wise, being able to firewall, your data and your map of the building is going to be important. You don't want bad actors to be able to hack in and download a map of your building from some centralized, public cloud instance or something. And so, there's definitely some challenges in this that we're taking a look at, and we've got a couple of great people doing that. And we hope to, when we start publishing some of our standards work and also some of the technical artifacts that we plan on building, you'll start to see how that's going to function. So privacy and security, we think spatial partitioning will kind of serve as natural barriers or firewalls. It also helps with the ownership of the data. So if I own an airport, a military base, something like that, it gives me absolute control of the definition of the inside of my space and even my campus outdoors. It allows me to control the access to that. So if you walk into a building, I can say, yes, you can download the map of my building. I'm gonna allow you access to that today. And we kind of think that decentralized ledger technology, blockchain, for those who don't know, may play a role in this, in securing. We don't think it's the absolute only solution, but it could play a role in terms of auditing access and controlling access. So to summarize real quick, maps we feel are going to be very important to share or store and share in standard formats. And we plan on doing that at least initially in using GML from Open Geospatial Consortium. We're going to need a common language for dynamically modeling reality. Interoperability and bring your own data, very important concepts to us. Spatial partitioning, we think, is going to play a critical role to privacy and security. And so with that, real quick, this is an announcement we made on Wednesday at our symposium. We're going to be working on, in 2020, what we call our open spatial computing platform. And some of the standards we're working on, I've already spoken about today, GeoPose, which is actually underway with OGC, and we have a working group forming around that very soon, I believe, right, John-Eric?
There's a vote among the members of OGC right now.
Oh, okay.
There's a lot of yes votes, so we are very
Okay,
optimistic.
so they're voting on whether or not to form or ratify the working group for GeoPose standards. So that could be coming very soon. GML is already existing and is going into its third iteration. And then RML is something that we're just starting to work on. And we hope to be publishing some of our early kind of versions or designs around that early next year. We also kind of, we're thinking about this thing called GLTF. So everybody knows what GLTF, it's a geometry 3D model format for the web. And so we're looking at augmenting the standard with geospatial information and geopose information so that when you query an object's geopose, it's already it's intrinsically tied to the geometry of that object, the virtual geometry of that object. Protocols. So Spatial Discovery Service protocol. This is to discover where I'm at. This is where I'm at, GeoPose, and then what's around me is Spatial Discovery Service. GeoPose request and response, RML subscription, the reality service, and then we're looking at some others that we haven't concretely decided, but scene understanding and spatial data. One of the concepts behind this is something that we call continuous contextual search. And if you can imagine, if you're, let's fast forward in 10 years, and we all have AR glasses instead of phones. I have some kind of an agent that's acting on behalf of me, and it knows about me and what I'm interested in when I walk into a building. It can contextually subscribe to the RML formats of those types of objects that I'm interested in. So those are the things that we're planning on working on coming up here in the next year. And if you're interested in joining us, that's our call to action in this. So we definitely need partners who are building technologies around AR Cloud to talk with us. We need to know your needs, your thoughts, and the technology you're building. We'd like to partner with you on that. And also passionate individuals who share the vision that we have and that some of the other visionaries in our industry have around what AR Cloud could be and what it could provide to humanity. So, that's my presentation. Here is some information on how to get a hold of us. OpenARCloud.org is the best way. If you're interested in looking up some of the standards that I mentioned today from OGC, you can go to opengeospatial.org and go to the standards tab and take a look at those and start reading through those. If you're a spatial nerd like me, it's a good read. And I wish I could spend a lot more time talking about them because they're actually they're pretty fascinating. And that's it. Now I think Q&A.